thanks everyone for coming. I'm happy to have you here in person on. Hello, Mark. On Zoom. So I am Daniel Wynn, the CEO of Mithril Security, and we are a recently founded startup that develops open source solution for confidential AI, and we'll present you one of our solutions. This webinar will be recorded and available afterwards. But the interesting part, I guess, is the whole presentation and the Q&A that comes afterwards. And so now, let us begin. So, okay, maybe not. Okay, so little issue. So as you know, AI is revolutionizing a lot of fields. We see it happen in healthcare, in finance. We see, for instance, the development of GPT models that are revolutionizing the analysis of human speech. We have seen AlphaFold, for instance, in biology. But there's an issue around how do we get access to more data, confidential data, to help train our AI models. And there are scenarios where having access to data can be complicated. Imagine, for instance, you want to detect, let's say, breast cancer from medical images using AI. There is an issue with the fact that data is often siloed in several sites. And we still want to provide a way to train an AI model on those multiple sites. But how do we do it while preserving the privacy of this data? Especially, imagine we have like 2 hospitals that want to collaborate on that project, and we have an AI provider, let's say a startup, that has the scientific knowledge to help the hospital A and B get onboarded with this. So there is a solution that you might have heard of in the machine learning literature, which is called Federated Learning. It was initially designed by Google, and the idea is that we want to train this AI model on those multiple datasets, but we don't want to make the data move because of security and privacy reasons. And that is why the idea is that the AI provider will make the model move and not the data. So in the first step, the AI provider dispatches the model to a kind of aggregator, which then sends the model to each hospital. Then each hospital can train their model locally, get some gradients, some updates of the model. We send it back to the aggregator, which then averages those updates and then redistribute the newly trained model. So this looks very good on paper, but you can see that there are a lot of errors, and this complexity will have actual impacts. So there are 3 main issues with most vanilla federated learning solutions. The first one is deployment. You saw before that each hospital had to train the model locally, but this means they need to have the hardware and software stack to train their model, and it can be a huge issue because imagine you want to train a GPT model, even let's say the 20 billion one. It will be kind of complicated to move huge racks of GPU and CPU on each hospital. And imagine you have 10 hospitals that want to participate, then the cost of deployment is huge, and so is the cost of maintenance. Also, you might have seen that the gradients move a lot, which can be a huge issue of communication because that requires participants to communicate a lot, which can be a huge bottleneck for the training of these models, especially if you start to train models that have several billions of parameters. That means that for each iteration, you make like gigabytes or even terabytes of data just to do one epoch. And then in vanilla implementations, you can also have security and privacy issues, because even though the data is not sent in clear, it can move disguised in the gradients on the model. Because there have been papers that have shown that by observing gradients, it can be relatively easy to reverse engineer the data that was used to compute those gradients. And also, there can be issues if people put malicious data or deviate from the protocol. So that's why they are That's why, for all those reasons, deploying federated learning in practice can be complicated. And that's why we are interested in providing a new way of doing this. But first, we need to introduce a technology that you might know of, which is confidential computing, which is the use of secure enclaves. So confidential computing is a recent field that helps secure the analysis of confidential data by using hardware-based trusted execution environments. And the idea is that those, what we call TEEs, have two big properties. The first one being that data is protected while it is being analyzed by a TEE. We'll see how. And the second one, which is quite interesting, is what we call code attestation, which means that we can have a cryptographic proof that only a code we know and trust will be executed on our data. And this will be a key piece to create the security of the whole system. So what does it mean that there is data protection during analysis? The idea is that whenever you have sensitive data that you want to have analyzed by a third party, you can have them use a TEE so that your data is not accessible by them. The idea is that whenever there is sensitive information to be handled, you will handle that inside this trusted execution environment, which is a kind of black box. And this black box has certain properties, such as hardware isolation or encryption of memory, so that whenever your data needs to be handled by that person, it is only done inside this environment, so that they cannot pick and see what is your data while it is being handled by this environment. Your service provider will still be in charge of bring the data inside this secure environment, but we'll see how we can do it securely. So first thing is, now it is possible that third parties analyze your data without seeing it, thanks to this hardware protection. But that is not enough. Even if we use a trusted execution environment, even if someone else in the cloud uses secure enclave, how do you know that first they have one? And second, how do you know that they don't put malicious code inside this trusted execution environment? So that is why there is a mechanism called remote attestation. And the idea is that it will help you gain both of those knowledge on both of those things, which are prove that the remote party uses a TEE and that they have put the right code inside. So even before you send data, the client, imagine you tomorrow, who wants to, or a hospital who wants to send data to a third party that has an AI model, you just ask them, prove me you are who you say you are before you send any data. And then the enclave, the trusted execution environment, has some the ability to create a kind of report that says, this is my ID card, I am a good enclave, look at me. And the idea is that they will sign it with a key that is derived from an embedded secret that is written on the hardware. And this secret is tamper-proof, which means that if I use a secure enclave to analyze your data, I cannot extract the keys that will be used to sign those identities. So that then this certificate is sent to the hardware provider. Those are hardware-based solutions. And so, for instance, imagine you use Intel CPUs. Then Intel will have a list of all the CPUs that they have created on the associated key, and they can verify that a specific enclave signature indeed comes from one of the hardware. And then they can stamp it and say, this is a legitimate enclave that is actually using the right hardware. And then you send it back to the client, and then it says, oh, like, okay, according to you, Intel, I'm talking to a secure enclave that has the right security properties, and also that has the right code. And how do we know there is a right code? During the generation of the identity, we have a hash of the code that is loaded inside the enclave that is signed in the whole package. And thanks to that, the client will see that there is a specific code that produces a specific hash that is loaded behind the scene. And we can use this whole thing to actually see how we can create, for instance, what we call an attested TLS channel, so that you can communicate secrets to a trusted execution environment for them to analyze your data without them having access to it. So, for instance, what happened is, okay, imagine the client is hospital that wants to have an AI model trained on the data. The host is, let's say, the platform provider, and the enclave will be used to train the AI model. So the first part is the hospital says, okay, I might want to use your infrastructure, your knowledge, but because my data moves to you, prove me first that you are using a secure enclave. Because if there is not that level of protection, I'm not going to send my data. So that's phase one. Then, let's say the startup that provides infrastructure, they say, okay, I will have my enclave prove you that it's indeed an enclave. And then it will generate the identity as I mentioned. They will send it back to the hardware provider, which can be like Intel, AMD, NVIDIA, depending on the hardware you use. They will do what I mentioned earlier, which is sign it after it checks some properties, like if it is indeed one of the hardware. And then the startup will send it back to the client, which is the hospital. The hospital say, okay, now I have a kind of report that says, this is the code that is inside, those are the security properties. And there is, inside this certificate, there can also be elements to do what we call a key exchange, so that the client can create a secure channel inside the enclave that is not accessible to the outside. And so at the end of this setup phase, the client at the end knows that they are talking to a secure enclave with the right code, and they have a secure communication channel, and they can send information for it to be analyzed. So that is a lot if you don't know a bit about how it works. But for the fun, if you want, I have a little Gradio demo. If some of you like to use Gradio, that shows a bit how it works. If in the assistance you want to try it, you can. There's a little QR code. I will let you do it if you want. And those who are online, you can just find it on Hugging Face Spaces under Blind AI to see what it means in practice to secure enclaves for AI. I will wait. So, do you guys see my screen? Do you see it? For those who are not doing the thing, okay. So this is a demo we have posted on Gradio. So this uses Blind AI, which is an AI deployment solution. The idea is that this demo shows you what it means to use a secure enclave in practice. So to give you an idea, what we did is that we deployed 3 kinds of servers. One server that does not use a specific hardware. For instance, here we're using the Intel Xeon processors for our secure enclaves. Then we have one enclave, but with a malicious code. We have put a print inside to leak information that is received. And the third one is an enclave with the right code. And so what happened is, if I try to communicate with a server without an enclave, we cannot move further. It's like when you have a browser and you go on a page that does not use HTTP, the browser says, no, this is fishy. So this kind of stuff that our solution can detect. Here we use behind the scenes an open source Python SDK on the client side that will do all the verification. That is why we are able to detect that kind of thing. You can actually verify the source code that was used for this demo. But here, at the first step, the code is not good. I mean, there is no proof that the remote server uses a secure enclave. Then the second one is actually using a secure enclave, but we added a little line of code that changed the hash that is measured inside. And we expect a certain kind of code inside, but it's not the one we observe. Because there's a mismatch between what we expect and what we observe. This is something fishy, so we're not going to move further. And then we have an enclave with the right code inside. There is, in the Python SDK, there is we have hard-coded the hash of the code we expect on the server side. And if we don't see it, then we stop. But here, because we see it, we can move forward. And also, yeah, the server side is also open source, so you can verify it yourself and get the hash yourself to see if it works. And then, for instance, once this is done, it's like HTTPS, which means it's transparent. You don't see that it happens behind the scenes, but it does. And for instance, we are using a GPT-2 model here to do text completion. Wow, it's amazing. Okay, it's just GPT-2, but it works. There is an AI behind the scenes that you can talk to, but with privacy guarantees that the people who operate this don't actually see your data, because there's hardware isolation of data so that they can peek into your data. So that's the cool thing with Secure Enclave. And I hope this short adventure have opened your eyes about what it can do. But this is for deployment. So now let's talk about, okay, just a little thing to get more, oopsie, to give more insight about where we are at. Il y a des gens qui attendent. Tu veux les voir? Where we are at in confidential computing before we continue. You might not have heard of it because it has been kind of immature so far. Because, for instance, Intel SGX, which is one of the first solutions, has been published in 2014, but it had only limited memory and the computation power was not big. But you can see there is an acceleration in terms of trends. AMD has come into the game, the major cloud providers also, and NVIDIA as well. NVIDIA providing Secure Enclave is a huge step forwards, because before we only had CPUs, which means for training of AI models, it was quite limited. But now, as we will see, it's possible to use Secure Enclaves with GPUs, and this means that it opens a whole new perspectives on confidential training. So now let's talk about the main topic, which is how can we train models on several parties' data with privacy? And it's simply the use of confidential computing in a multi-party training setup, and this is what we call fortified learning. So the difference now is we are not using a decentralized approach, because decentralization comes at a cost of efficiency and speed, which might make it very hard to deploy in practice. So the idea with fortified learning with BastionAI is that now you upload the model and the dataset inside the secure environment. So it becomes centralized, but we use the security properties of the TEE, of the secure enclaves, to still protect users' privacy, data privacy. And now you just need to upload the data once and the model once, and then you train inside this cluster. But so as we will see, by doing this, we can solve a lot of issues. First one being, now the hospitals, they don't need to install the GPUs, the CPUs, and all the hardware and software stack, because they just need to do the attestation of the remote enclave, and then they can dump data encrypted there and have the computation done externally. But that means that it's much easier for them to be onboarded. You can imagine that they have a similar web interface where they just verify the property from the browser and then drop that data. But that means you can now have confidential training as a service. You don't need to have like your people come with trucks of GPUs and install everything. Now they can do it remotely, quite easily, but still with a high level of security and privacy. Big point also, there is much less communication needed, as you can see here, because you just upload dataset once. It's a fixed cost. You don't need to communicate at every round. So this makes it much faster. And also you can concentrate in one node all the GPU or the hardware to do computation, instead of having to require it on everyone's infrastructure. And finally, the only communication is within this cluster. We can have a cluster of GPUs that communicate between them here securely with the TEs, but it's only inside this closed network. It does not need to be sent over long distances, let's say. And finally, with secure enclaves, we can preserve model and gradients through encryption, so that no participant can see the model and the gradients. And also, as I mentioned, with remote attestation, we can have integrity of the data and the computation, which block certain sides of attacks. And so the workflow is quite simple. first you upload the dataset inside this enclave. Then the data scientist sends the computation they want to do, and computation is performed inside the enclave, and then we get the results. So let's see an example of how it works in practice. So I'm just going to show you the notebook because my machine has Zoom and a lot of things working at the same time. But you can find the code on our GitHub, which is open. So this is just a little example of how you can train, or more exactly, fine-tune a DistilBERT model on a small data set, the SMS spam collection, with our solution BastionAI. So the first idea is that you can install the PyPy package, quite easy, and it's just some like dependencies here. So the server can be run using our Docker image. For security, you can deploy it on AMD SCV SNP if you want to run it on here real hardware that we support. But you can also run it in a more like simulation mode if you just want to try. So here we just get the data set. Okay, so how does it work? There is an offline phase where the data owner prepares the data set to make it available in the PyTorch format. And the data scientist prepared their model also to be available in the PyTorch format as well. And then there is an online phase where they communicate and upload their information. So here we look at the point of view of the data owner. So here I get some data set with text to classify if it's a spam or not. Here we do use some DistilBERT tokenizer to get the data set available. We create a tensor data set, and this is what we will send to BastionAI. Then for the data scientists, they just need to prepare their model. So here it's a DistilBERT model. We need to do little something to make it work with our stuff, but it's just some technicality. So once the data set and the model are available, we go in an online phase. So here, the data owner first uploads the data set. So when we call this lines of code, what actually happens is that we perform the remote attestation. We make sure we talk to a secure enclave, and then we send data encrypted to that secure enclave. So here we upload the training and test set. And something I didn't mention is that BastionAI also supports differential privacy by design. So here, for instance, the data owner can define how much differential privacy budget they allow to people to train on the model, on the data. Okay, here I put 1 million. It's not very relevant, but you can put smaller budgets. Then the data scientist can connect to the secure enclave and see what are the data sets that they have at their disposal. The idea is that here they only get they get local pointers to remote objects, but those are only metadata. So data scientist only has access to metadata that are inside those pointers, but they never get access to the data set in clear. But this metadata can help the data scientist to the right parameters to train their model. And then once they want to train their model, they create what we call a remote learner, which is inspired from past AI learner objects, where they provide the model that they have, which will actually be uploaded at the end of this instruction. They say exactly what data set they want to be used on, and some parameters like personal entropy, etc. And then when the .fit method is called, it actually triggers the training inside the secure enclave. So if I come back to this, that means that first we send the model into the enclave. The data scientists uploaded their model and they specified the ID of the dataset that was uploaded before. And then they send an instruction when they do fit, which triggers the training into the enclave. And for instance, they can specify how much differential privacy they want to use for this. We can get a testing metric at the end, and if the data scientist has the right to, they can pull the weights of the model locally to have access to the model. So that is how it works with our solution. So let me get back on this. So, okay, so that's how it works, which is actually functional. You can have a try on the GitHub repository. And so that's a little bit how it works. So as I mentioned, you have the Python client that does only the verification, send data, and things like that. And then inside the secure enclave, with this kind of interface that is specifically designed to do the training of AI models on several datasets, but it's quite limited. This interface communicates with three main pieces. First one is a differentially private computation engine. As you saw here, it's using PyTorch. And we have some specific modules that we have developed to incorporate differential privacy. There is all that is around attestation, identity, and integrity of the process. And then there is some flow governance. And flow governance is who gets the results, who has the right to get the model, for instance. And that is what we have behind the scenes. So to see the performance, because that's actually what is interesting, we have done some benchmark on EfficientNet that is soon to be available. And we are also trying, we're also doing currently a benchmark on training a GPT-Neo model, I guess with like 3 billion or something like that parameters, to see how we can actually use BastionAI on state-of-the-art models and still preserve privacy for users' data. So here we are using an AMD processor because those are the ones that are currently available with the secure enclave technology that we're interested in. It's what we call confidential VM. And here is some initial benchmark. So here we're using PyTorch alone to train the EfficientNet model. This is like the time it takes to do one epoch. So it's a CPU, so it's not like the greatest thing. And you have the batch size. And then you have PyTorch with what we call Opacus, which is PyTorch library for differential privacy. So you can see that there's a huge overhead when you want to add differential privacy, which makes sense because you need to modify the backpropagation and things like that. Then it's PyTorch with Flower. So Flower is a federated learning library of PyTorch to train a model in a federated approach. Here we used 2 nodes, so 2 people participate in this. And then this is PyTorch with the whole package, federated learning and differential privacy. So you can see that it becomes quite big. The bigger, the less interesting. This is the time per epoch. So it's like 10,000 seconds. So that's that's a bit long. And then here is BastionAI, so our solution. So you see that we are 20 more seconds slower than PyTorch alone. And if we add differential privacy, we are still 6 times faster than PyTorch with differential privacy. But the interesting part is with GPUs. So little issue, the GPUs of NVIDIA with the secure enclave abilities will be available at the end of the year and stuff like that. So it's not available right now. So we did some experimentation with non-secure GPUs, but we'll provide benchmarks soon with the secure ones as soon as we get our hands on it. But so here now it's like more interesting. I mean, so still PyTorch is 7 seconds in the baseline, so one machine, etc., without any privacy. Differential privacy, you see it's much bigger, and then here with 2 nodes, it's like 26 seconds. And so PyTorch on 2 nodes that each have their GPUs with different privacy is like what? A lot. Yeah, like almost 40 times slower. And with, in our case, it's 11 seconds. So 11 seconds is compared to, so BastionAI is interesting to compare with the federated learning approach. And here we're like what, 2.5 faster. This is 2 nodes. We haven't done with more nodes. And we expect that with the more nodes there are in the process, the slower it gets, but we're still doing the benching. But still, it's like 2.5 faster. And this is we haven't like tried the huge models yet, where the communication will be a bottleneck, and we expect to see a bigger overhead with GPT Neo models. This is EfficientNet. EfficientNet is rather small. And finally, BastionAI with differential privacy is still like 3 times faster. Question afterwards, but just write it down. Actually, we're done. So yeah, just little things to end. Yeah, so we are open source projects. We believe it's important to be open source to help democratize these technologies. If you're interested, you can go on our Discord, where we sometimes often post, but okay, whatever. And there is a GitHub repository for both the deployment solution, which is production ready. So you can deploy models, for instance, such as Whisper from OpenAI with privacy guarantees, and also BastionAI, which is a framework I presented today around confidential training. So that is it. Okay, so I guess I can take questions now. So I don't know. Can you record? Yes. No. I just tell them to ask questions, but then I will take Mark's questions. Okay. So yeah, Mark can. Okay, so question for the engineer who was in charge of this. Okay, so just okay, come here because people. So the question is, why did we change the batch size? Which is a good question, actually.
So actually, solutions like Opacus consume a lot of memory. So the full batch size we use, for instance, with the baseline couldn't fit in that memory, so we had to reduce it in order to perform the training. So that's why we basically the points that are in that graph are the best possible batch size you can achieve. So either it's with the maximum batch size that fits in memory, or the fastest setting. So yeah, that's why the batch size changes.
Yeah, I mean, we could have used the same one for the baseline, I guess, but otherwise you see that it matches for 4,000, 4,000. So
it's smaller for your solution with the differential privacy than with.
So that's because we may have a better memory model than Opacus, for instance. At least that's what the benchmark suggests.
So it couldn't fit in memory with Opacus, and I guess we got something better. So we put. I mean, we could have actually, yeah, we could have put the same batch. It was just, you know, we just wanted to see what is the biggest one that could also fit. But I guess for full, yeah, match, we could do it again with the same batch size for everyone.
Here, the goal was just to compare the best settings for each solution. So that's why we vary the best.
Yes. Other. Yes.
My question was more inside your BastionAI. Why do you need more memory for differential privacy than without
differential, what it requires more? You said.
You said that you are decreasing the batch size because of memory constraint.
Yeah.
So I guess for your DP solution, you are requiring more memory.
Yeah. Yeah. DP requires more memory to. For the DP-AGD algorithm, well, you can explain, I guess.
Yeah, that's the same issue than with Opacus. You have basically to retain the gradients for each sample in the batch in order to compute the DP updates. And so it takes n times more memory than usual backpropagation if the size of your batch is n, of course.
Yeah. Okay. Other questions in the is it, yeah?
A question more from the infrastructural side. How are you starting the AMD SEV, if I understood well? How do you spawn it and how do you initialize it? What do you put inside? I guess you need the Python runtime, but you need also some other trusted compute base that can then enlarge and be also an attack vector. And then also, how do you handle that, you know, those parties that upload data, you know, they cannot see each other's data, or, I mean, I know how it is done on technical level, but on the procedural level, like we have a client, so that one enterprise uploads data, then another one, then they get notified, then you start kind of computation and bring back the results and so on.
Okay, so the first part is how do we spawn it? I mean, how do we spawn the? I mean, what do we put? I mean, what's the process? I guess.
Yes, like how do you spawn the VM? You know, do you use, let's say,
You wanna?
some AMD kind of SDK, or
Yeah.
because there are a lot of now libraries appearing on the market and are
Yeah. Okay. Yeah. So Shannon, our engineer, will come and answer that. But basically, just to give some preamble, like we use the AMD and SCV solution available on Azure to do this, and Shannon will finish.
So currently on the market, like with cloud solutions, there aren't a lot that implement AMD SCV the way AMD initially wanted, because passing control to the user that early in the boot process is kind of an issue for most cloud providers. So what Azure has done is they have figured out a way to sort of create another init ID so that they can just push the user directly into it. So we have essentially we don't have an SDK, so we can make an IOCTR call directly to the processor to retrieve the report. So for the spawning in terms of Azure, like how they do it is like when you boot, they have these confidential VMs. I'm not sure if I can talk about that.
Sorry?
Am I able to talk about the
Good question.
Yeah.
We did something, I guess, that was closer to AMD Spirit instead of relying on Azure, I guess.
Yeah. So yeah, essentially with Azure, you have a solution that lets you boot directly into the VM, and it hosts, like, don't look into the host process of how the host boots into it. But yeah.
So
you have a more specific.
Yeah.
No, I was just like, I was interested in it kind of on some hosted cloud like Azure.
Yeah, it's Azure.
Or it was on a kind of premise, because when I was looking at the hosted solution, they had some problems, at least at the time, with attestation.
Yeah.
Yeah.
So that one it depends on another.
Yeah. So we tried like pretty much everything, every provider that was available, and like everybody has an issue with attestation at the moment. So Azure is the first one that we've come across that has currently implemented a way that you can directly retrieve the hardware report from the processor, which is not something that anybody else currently provides, but everybody, as far as we know, is working on it. But they have not yet launched with like a hardware report retrieval, except for Azure.
Yeah, we're doing tests with OVH, but not over yet. So that's the first part. I guess the second part is like, what do we put inside? So the idea is that we try to limit as much as possible the code inside the enclave. So we just put, just put PyTorch. But with, as you saw in the demo, there are very few endpoints that can be used. It's not like we allow people, oh, put a Docker image. Then you say, okay, well, like there are thousands of things that can happen here. So it's just data scientists can only do two things. I mean, upload the model, get the model started and pull the result if they have the right to. So they cannot always do it. So they have just like 3 endpoints. And you can then, look at the code and verify that the endpoints do what they do. But to try to minimize as much as possible the code that is inside. And so it's both for issues of security, but also for ease of use. So now people, it's, it's not like they have to deploy something. You can actually, I can show you like what we have done with the deployment solution, but everything can be handled within the Python SDK. You just don't even have to like, manage the whole thing. So it's not only good for security to minimize as much as possible what you can do, but that also means you can provide an easier to use interface. But then the issue is, we work a lot on privacy and security. Our team works a lot on making the surface as small as possible. We just put enough to do what we need to do. But then all other operations, for instance, users can only upload torch script models. So it's already it has already a limited set of operators that are allowed. So like we try to minimize as much as possible, but still provide something that is quite flexible enough to cover the use case they want.
Just one more question. I don't want to monopolize this. One question regarding what you put inside, and okay, with trusted execution environment, you will protect this from the outside world, from the host, and then malicious, stuff there. But within the enclave, if I'm allowed to, let's say, execute my algorithm or train my model on somebody else's data, how do you prevent my algorithm stealing this data, simply copying them outside? Is there some kind of protection within the, let's say, algorithm, or do you force and enforce, and I don't know, from the differential privacy, which you don't then use probably in
the question is, how would you, within our current framework, it's not like you have you can send Python script that's where you can write copy data. Here you just send PyTorch models, which are like what neural networks. So the question would be, okay, so the only thing we allow people to do is they train a model. So, and the code can be expected. So like, are there specific model architectures that when they train on some data, naturally learn how to copy paste data? That I guess could be, possible. So I guess there are several ways to mitigate this. First one is, for instance, we could ask the data scientists to share the the infrastructure of the architecture of the model, so that at least it's I don't know how you, I guess there are ways to try to design neural networks that would be better than others to copy paste data, but I don't know. I mean, but first one would be like first asking them to share the model architecture, I guess. You can also put differential privacy that provides more better guarantees about the ability to not remember one specific record. So I guess those are more or less the things we can provide to make it less likely that a model learns by heart a specific, because it's not like this is the only attack vector that we have to because otherwise it's not like we allow people to upload any kind of workloads. The only payload you can put is a PyTorch model. So
that's the problem, because this model or this algorithm can actually be done on purpose like that it steals the data from within the enclave.
Yeah.
It just copies it and returns the result. And that way, kind of breaks the system where you are building this
actually
around it to...
Yeah, I guess there are ways where you could define a training. I mean, would a model train to just classification, let's say spam classification, and you can only allow them to say yes or no to some task, and would the model be able to learn by heart specific? I mean it's maybe, I don't know. I mean, I guess it depends on the task at hand, and also what do you enable people to do? I guess it is theoretically possible, but actually it's a good question. We might have to look at the literature about how people try to design neural networks that through gradient descent learn by heart a specific thing, especially if you do. I mean, it's not like the task here is about. It's not like we do have an autoencoder or whatever that's taught to reciprocate some data. Here, for instance, if you do classification, I guess there will be theoretically some things that are possible, but in practice, can a model train just to do spam classification learn to gradient descent on a private data set that yeah. Okay, so I guess in that that would definitely need the differential privacy at that case, because this is actually an issue. It's actually the case, for instance, with language models that can learn by heart, and there have been papers that have shown that if you use differential privacy, let's say smartly, the ability to pull out data becomes much harder. It's not impossible, but that's the best thing you can provide, I guess. Yeah.
We have a question. I will try to ask if you want to ask it on.
Okay, just or just read it. I mean, did the girl raise his hand or just ask the question?
Yes. For attestation service, what did you measure to verify the integrity of the enclave?
Shannon, you want to come back? I didn't do it. Yeah.
Okay.
So did you hear the question? I mean, so
so
can you repeat the question so that people know?
Me?
Yeah,
Oh,
repeat the question as
So
well.
for attestation, what do we measure to ensure the integrity of the enclave? So is that for BastionAI or BastionAI?
BastionAI, I guess.
Okay, so for BastionAI is we consider the enclave to be the entire conventional VM. So what we do is we get we make an image tree like a root tree for all the contents of the image, and we get a hash at the end. So we know exactly like a hash, or we have an idea of every single file that was in the image prior to boot. And also, just like we ensure that people know what is within an internal enclave, we also make sure they know what is within the image. So for that reason, you also have to provide the image so people can check to make sure that they know what is within the image and they can verify that the hash matches what they use.
Yeah, so for all our stuff, be it BastionAI or BastionAI, provide open like scripts for people to recreate the image we put in practice so that people can verify themselves and check it. Okay. Are there other questions? Is it clear for, is it good for everyone? Give a little bit of idea of the future. Today we put the differential privacy, it's available, but we are starting to put some stuff to do access control so that it was not shown, but there is like we want to do stuff where the data owner defines when they upload the data set who can actually train a model on it. And for instance, they would pass some public key so that we can force that only specific people can do specific things. So this is the next thing we will do. And we'll also cover some, we work soon to have a cloud solution so that people can actually, we manage the hardware so that people won't have to deploy their stuff on AMD ACV on Azure. And still we try to not to be out of the loop because we still is. But the idea is that we want to make it possible for users to spin a session with BastionAI enabled, they do 1 hour of training, and then they can close it and manage it so that everyone can use it easily. So that's the next steps if you're interested. And yeah, we continue. We are also working on a white paper. You can also have a look at that. I mean, there's an article that explains things we do in more details on our blog for BastionAI, but we'll also do a white paper around our stuff. So that's
what do you expect from those NVIDIA GPUs with the teams that you mentioned? How do they work with the CPU key?
Yeah, so far it has been let's say the most production ready thing would be this one, because this is actually working. The NVIDIA attestation mechanisms still have to be developed. In our case, we don't have that yet, but also because the hardware is not fully available yet. But the big use case is to also have the attestation of the GPU. No, the CPU is working. Then the attested CPU will have to attest the GPU. But when it's done, it can open a lot of things, because then that means that, for instance, you can train huge models on text, on images, like for medical imaging and things like that. And so that means that, for instance, we're discussing with some company that uses NLP models to analyze medical text, but they have been limited by the ability to deploy hardware on-premise because it's for hospitals. But that means that now they can deploy even like GPT models for those use cases, because it's much easier for them to send data to the cloud or to do confidential training between multiple data. So having the GPUs would mean, we'll be able to, for instance, try how does it work to have a GPT with 20 billion parameters on several hospital corpus of documents. So that's the kind of stuff that we want to enable, which I guess is pretty hard if you use standard solutions. Okay. Good. Okay, thank you.